Hello and good morning from Rocket Lab. Electron is back on Pad A for the first time in 2 years from Launch Complex 1 in Mahia, New Zealand, as we prepare for our 53rd launch with return customer Kinéis. The countdown to liftoff is currently scheduled for 11:01 a.m. local time or 23:01 UTC. My name is Prachi Saknani, and I'm joined by Andrew Haig, and we are live from Mission Control in Auckland, New Zealand, as we carry you through the final minutes of today's launch operations.
Thanks, Prachi. It's great to be here with you this morning, and it's great to be here with you watching at home. You're looking at a live view of Electron, as we are currently 17 minutes and 35 seconds away from liftoff for today's mission. Kinéis killed the RadIOT star. A riff on the 70s music hit Video Killed the Radio Star by the Buggles for French Internet of Things company Kinéis. It's super exciting to be back on Pad A after 2 whole years, and we introduced our second Electron launch pad, Pad B, at LC1 back in 2022 to enable some upgrades and maintenance to be carried out on Pad A. Pad B is our third pad overall, including our launch pad in Virginia on Wallops Island. But today, though, Electron will take to the skies using Pad A's upgraded control system and refreshed hydraulic and fluid systems as part of the pad's glow-up.
Today's launch is the second in a series of 5 dedicated Electron launches for Kinéis, an international space-based solutions provider to improve global Internet of Things connectivity. It was only 3 months ago that Kinéis launched their first mission, No Time to Lose, to deploy the first of their satellites to space on our commemorative 50th Electron launch. Let's take a look back at that mission.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
Just like their first launch with us, this launch is tailored specifically to meet Kinéis' mission requirements, providing them with control over their launch schedule, orbit, and deployment parameters, more so than would be possible on a rideshare mission. Now, today's launch will deploy Kinéis' 5 satellites in a precise sequence, first as one and then as pairs, to build out the constellation exactly as they need it. Now, let's hear more from the team at Kinéis.
Kinéis is a French company based in Toulouse. We are a satellite operator and a global connectivity provider dedicated to the Internet of Things. Mountains, ocean, deserts. 85% of our planet has no network coverage. In 2020, we raised a large amount of 100 million euros to address this global issue. Today, we are following through and will deploy a constellation of 25 nanosatellites that will enable us to connect to a multitude of objects anywhere on the planet in near real time. We are convinced that this transmission of information made possible by satellite connectivity will enable us to respond to crucial challenges for mankind, its activities, and its environments. On the environmental front, for example, Kinéis connectivity can detect a fire outbreak in less than 15 minutes, thus considerably reducing the extent of the outbreak and reducing the loss of property and human life. The same goes for monitoring water levels to prevent flooding and use this dwindling resource. The applications are endless, whether for locating, monitoring, or alerting. Since the creation of Kinéis in 2018, our teams have been working with this objective in mind. Our 25 nanosatellites that weigh only 28 kilograms are real technological gems. The retractable UHF antenna, for example, can hear a bird sing within a rock concert 650 kilometers from the Earth. We fitted them with thrusters to ensure they stay on track for their mission. Some even carry children's drawings. That's amazing. At the same time, we have deployed many ground stations worldwide and have a sovereign infrastructure to guarantee data transmission to our clients. Today, Rocket Lab is preparing to launch a new cluster of 5 satellites, marking yet another significant step forward in our mission. With 5 satellites already in orbit at 650 kilometers, each launch reinforces our ability to connect with the rest of the world and address the challenges essential for people, their activities, and their environments. We can't wait to take this next step.
We're excited to get the second set of Kinéis nanosatellites to orbit. This launch will bring Kinéis' total to 10 satellites in space, getting them closer to their goal of 25 in the full constellation. Kinéis has 3 more dedicated launches with Rocket Lab to deploy the remaining satellites that will help provide their customers with precise connectivity and location tracking of any object anywhere on the planet.
All right, we're approaching the T-minus 12-minute mark at LC1. Now, next up is one of the final status checks before liftoff, the go, no-go poll from our operators in mission and range control. Let's listen in now for the calls and see if we get greens across the board to proceed to launch.
All stations, LD on mission, proceeding with the go, no-go sequence. Stage.
Stage is go.
Avionics.
Go.
GNC.
GNC is go.
VCon.
Beacon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
And LD SUP.
LD SUP is go.
Okay, go, no-go sequence is complete. We are T-minus 11 minutes and 19 seconds and counting. We are go for terminal count auto sequence at T-minus 10 minutes. From this time, the 3-word hold procedure is in effect.
And there it is, greens all round, and we are go for launch. You just heard the call out from Michael Pearson that we are proceeding today with the planned liftoff at 11:01 local time, now just less than 11 minutes away.
While today is all about Kinéis and Electron, the team has been busy developing our new and much bigger rocket, Neutron, including some big wins for automation. We've completed the install of the largest automated fiber placement machine of its kind into our Neutron rocket production line in Middle River, Maryland. The custom-built 99-ton robotic machine will automate the production of all large-scale composite structures for Neutron, including the tanks and fairings. Last month, we caught up with Mike Mason on how this will accelerate production, so let's take a look.
We excel in the production of carbon composites here at Rocket Lab. We've done a lot of R&D throughout Electron and space systems and now Neutron, so we know what we're dealing with and we can produce a really high performance light launch vehicle using it. This AFP machine is the biggest of its kind in the world. It's standing over 12 metres tall and can travel 30 metres back and forward along the work cell. We'll be tasked with building the biggest structures of the Neutron vehicle. This includes the 7-metre domes and barrels that make up the Stage 1 tank and some of the 12-metre long interstage panels that enclose the Stage 2. AFP stands for Automated Fibre Placement. It's essentially an industrial process that massively accelerates the laying down of carbon fibre onto a mould to build large carbon structures. This is a process that's traditionally done by hand. So the key performance metric of a machine like this is essentially how fast it can lay out carbon fibre. This is really important because our large parts are made up of hundreds of layers of carbon fibre and thousands of square metres. So the faster we can do this, the better. We can pay out over 100 metres per minute of carbon fibre. Currently it takes a large team several weeks to build a Stage 2 dome, whereas this machine will be able to punch it out in 24 hours. The machine's been designed to accelerate in any direction at 0.2 G. It's able to stop on a dime, turn its head around in a fraction of a second and start laying down carbon in the opposite direction. And it's little things like that that make this machine much better than the rest. This machine will be installed in our new facility in Middle River, Maryland. This is our space structures complex, which will be quite heavily focused on producing the large composite structures required for Neutron, but will also act as a centre of excellence for composites for the whole company. So that's including space system structures and Electron composites and all sorts. So this machine also includes a fully automated real-time inspection system. This is really important for composite parts because they're made up of so many layers. So it'll search for minuscule defects as it goes along and will notify the operators of any issues before it starts on the next layer. It means that we can sort of maintain our really high quality standards for spaceflight structures. Me personally as an engineer, I love machines, I love automation, and this is state-of-the-art automation. For the size of the machine, it's the highest performance thing out there, much faster at moving around than a traditional CNC machine, and there's some really clever smarts going on in the process to make sure that we lay down fast and accurate components.
If you want to work on cutting-edge machinery building leading-edge rockets, we have plenty of roles in our manufacturing teams across the entire Rocket Lab family. Check out rocketlabusa.com/careers and apply today.
LD avionics mission.
Avionics LD.
Avionics terminal checks complete.
Copy, thank you.
If you've been following us for the past 52 missions, you'll know all about our Electron rocket. But if you're joining us for the first time, then here's everything you need to know. Electron stands at 18 meters or 59 feet tall, and it's our dedicated launcher for small satellites. Now, it can lift a maximum payload of around 320 kilograms or 700 pounds, and it was the world's first carbon composite orbital class rocket, which is what gives it its signature black look. Now, we chose carbon composite because it's incredibly lightweight but strong, allowing us to maximize payload capacity. Before Electron's fueled, it weighs about 1 metric ton, but once the tanks are filled with liquid oxygen and kerosene, it weighs more than 12 times that.
Now, to get our customers to space, there are 9 3D printed Rutherford engines on Electron's first stage and a single vacuum optimized version of Rutherford on the second stage. There is a separate 11th engine on Electron known as Kinéis, with a much smaller but still 3D printed propulsion system that powers Electron's kick stage in orbit. The precise maneuverability of Kinéis allows the kick stage to raise and lower its orbital placement to perfectly position the satellites that it carries for deployment. Like many rockets, Electron stages operate a bit like a relay race. The first stage, the largest single structure of the rocket, carries the mission for the first 2.5 minutes of flight before it separates off the second stage. The first stage falls back towards the Earth, while the second stage takes over the race. The single Rutherford engine on that second stage burns bright for another 6.5 minutes, propelling us all the way to an elliptical orbit before we have another stage separation event for Electron, this time between the kick stage and the second stage. The final leg of the journey is then completed by the kick stage, which circularizes the orbit ahead of payload deployment.
At T-minus 2 minutes, the team in mission control are hands-off, with Electron's flight computer taking over the countdown and autonomously running through its final operations. Now, operators then pivot to monitoring their stations while Electron essentially launches itself. Now, liquid oxygen will continue to be topped off into Electron's tanks all the way up to T-minus 1 minute 30 seconds, and then we should hear a call out from mission control that the lock system is in recirculation. After that, we'll hear a confirmation that Electron's first and second stages are fully pressurized and ready for launch, and then all that remains is to listen out for the final 10-second countdown from the launch director. But now that you know what to expect, let's watch it all unfold in real time as we enter the final minutes of the count. I'll send you over to mission control, and we'll be back with you after liftoff.
All stations, LD on mission. From now there should be no red flags on your critical LCCs. Beacon LD mission.
LD beacon.
Please lock auto sequence and confirm.
Auto sequence is locked.
Confirm all expected flight computer ASGOs are green.
Confirmed, all ASCOs are green.
Okay, all stations, we are go for auto sequence start at T-minus 2 minutes. LD is go for launch.
Vehicle is fully on internal power. AFTS is green and ready for flight.
LOX load is complete. System is in recirculation. Anti-geysering is disabled.
Stage 1 and Stage 2 tanks are pressed for flight.
High flow engine purge enabled.
T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Had an abort. GC LD mission.
LDGC.
Please confirm the launch inhibit mode is enabled.
Confirmed.
And all stations at this time are proceeding with the immediate abort, or auto sequence abort checks, sequence 66. GC confirmed stage 1 and stage 2 umbilical statuses are engaged.
And negative LD working on getting stage 1 umbilical re-engaged.
Copy. GC sub LD mission.
As you can just see, Electron has had an abort. Let's throw it back to mission control and wait to hear more.
CO2 fire suppression system is active.
Copy.
If you're just now joining us, Electron has had an abort for the day at T0. Our auto termination sequence was triggered. We're now throwing it back to mission control as we wait to hear more. We're standing by for further updates from Mission Control, but since today's mission required an instantaneous launch, we'll be standing down from today's launch attempt. We'll share more across Rocket Lab's website and social media channels. Thank you for joining us. This is Rocket Lab Mission Control, signing off.